looking at energy systems, ATP, known as adenosine triphosphate. This is formed of one adenosine molecule and three phosphate molecules, and these each are bonded with a high energy bond. During the sliding filament theory, which is briefly shown here, basically the ATP is split into ADP. So one of these bonds are broken during the power stroke. So due to this change, there leaves an inorganic phosphate molecule, which means that there's a requirement to reform this ATP, as we don't want this ADP or inorganic phosphate molecules. That is how we need resynthesis of ATP. And this is done through three different energy systems. First is the PC, the Phosphate Creatine energy system. We also have the Glycolytic anaerobic energy system, and you also have the aerobic energy system. Now this shows the interplay of the energy systems. So in the first few just past 30 seconds, you can see that the ATP-CP system is working, and then once here it uses up all its energy, so it can't contribute any longer. But this is the dominant energy system until this point here, where the glycolytic energy system then becomes the dominant energy system, contributing to this high energy for about 2 minutes until it then drops again. And at this point here, that's when the aerobic energy system then becomes the dominant energy system. But notice that at the start, all three energy systems are working. It's just that the ATP-PC energy system is the dominant one at the beginning, and this changes throughout. Now looking at phosphocreatine, we have, this is usually known as the ATP-PC system, but looking at phosphocreatine on its own, it's made up of one phosphate molecule and one creatine molecule, and these are stored in the muscle sarcoplasm, and this is the simplest process, as it simply breaks the high energy bond of the phosphocreatine and uses the phosphate molecule as energy to create ATP, as ATP is the only thing that can cause muscle contraction through the sliding filament theory. Phosphocreatine, there's about this is used in maximal intensity, as it's the most readily available and the quickest and simplest process. However, there's a short amount of it, of only 7 seconds, and as it's shown, it was stored in the skeletal muscles, specifically the muscle sarcoplasm. The process of the phosphocreatine breaking down and then the inorganic phosphate being formed with the ADP to form ATP, this is known as a coupled reaction, as the breaking of the phosphocreatine is an exothermic reaction, and the formation of ATP is a endothermic reaction, and that's why it's known as a coupled reaction. This also only produces an ATP yield of 1, as there's only one phosphate molecule in this phosphocreatine per phosphocreatine, as it's such a simple process. Now looking at the glycolytic system, it uses glycogen from the triglyceride stores in the skeletal muscles, and then glycogen is then broken down into glucose, and that is through the enzyme glycogen phosphorylase. And then from glucose, it's then broken down into pyruvic acid, and that is done by the enzyme known as phosphofructokinase. And then the pyruvic acid, as there's a lack of oxygen, as there is no oxygen present or enough oxygen present, that is then transferred into lactic acid through the enzyme lactate dehydrogenase. And that it produces lactic acid, as it can't enter the Krebs cycle, so is left as lactic acid, as that is the furthest it can break down. This is done in high intensity and is the dominant energy system once the phosphocreatine stores run out. So after 7 seconds, this is then the dominant energy system. After 10 seconds, as the ATP on its own can be used for up to 3 seconds, and then the phosphocreatine system can be used for 7 seconds. So from 10 seconds all the way to about 2 to 3 minutes, the glycolytic system is the dominant system being used. However, this also produces a waste product of lactic acid, as that there's nowhere for that to go, so it causes a build-up of that. And lactic acid causes an increase in acidity, as there are hydrogen ions being produced, which causes the pH in the muscle cells to decrease, and once there's a great enough build-up, this inhibits the glycolytic enzymes from functioning properly. So this forces the body to reduce the intensity once the build-up becomes too much, and that's why there's a 2 to 3 minute duration of this. Now this can be measured through blood lactate, with a average resting blood lactate of 1 to 2 millimoles per litre, and then can reach up to or above 20 millimoles per litre on average after a high intensity exercise. You see that there's first the LT on this diagram here, and that stands for lactate threshold, and that is a point in which lactic acid first is being built up. So that is the rate of intensity at which the body can't break down lactic acid quick enough, so it causes a build-up of lactic acid. And then soon after you have OBLA, so that's the onset of blood lactate accumulation, and that is at 4 millimoles per litre. And once it reaches that is when it's known as shifting from being aerobic exercise from here to anaerobic exercise, as there's suddenly a steep increase in blood lactate accumulation in the muscles. Looking at the investigation, you can first look at the blood lactate levels during the multi-stage fitness test, and as you see, at rest this was about 2 millimoles per litre, and once we got to level 4, which was the middle of the test, that increased to 6 millimoles per litre. So already it's increased by 4 millimoles per litre and has passed the point of OBLA of 4 millimoles per litre. So this shows that they are now working anaerobically. And then as the intensity then increases once more, up to, I think it was level 8, where the test then ended, you could see the blood lactate levels were approximately 24 millimoles per litre. So a solid about 22 millimoles per litre increase since the beginning of the test, which shows how rapidly it can increase as exercise increases, as it's quite a shallow increase here, but then once it's past that OBLA mark, it's a rapid increase there. Now looking at the Wingate test, and see rest was approximately 1 millimole per litre of blood lactate, and then the post-test, that's about 15 millimoles per litre. And you can see in just 20 seconds the rate in which that has increased. It's quite drastic, and you can see in 20 seconds they're reading quite similar results of blood lactate to that of about 15-20 minute multi-stage fitness test, which shows the high intensity of this Wingate test and how hard people have to be working. Now, there are interplay of energy systems, so different energy systems will be working at different points in a game. So in a game of football, the ATP system will be the dominant system during a goal kick, for example, as it's very short, less than 3 seconds, very sudden, and requires a big amount of force to kick the ball up the pitch. PC system would be a slide tackle, as the act of running to alongside the player or up to the player, then slide tackling. That would be longer than 3 seconds, but not as long, not above 10 seconds. So it's still quite a short action which requires a lot of force to get the ball from the player. But so the PC system would use that as it produces high amounts of energy for the player to perform that slide tackle. The glycolytic system to be the dominant system, an example would be a counter-attack. So running from one end of the pitch to the other would require high intensity of sprinting, but obviously would be longer than 3 seconds or 10 seconds in total. So, which means that the ATP stores and the PC stores have run out by that point, meaning that the glycolytic energy system will then have to become the dominant system to produce the energy to run down the pitch and cause that attack and potentially through on goal to score. And because counter-attacks can be relatively short, but are longer than 10 seconds. So it'll be between 10 seconds and usually a minute, but potentially 2 minutes, but is unlikely.